Apart from the axiom of equality of sets, all other axioms of set theory are about um, opening up possibilities for forming various kinds of sets. So one such axiom is the axiom of pairing. It allows us to take two sets and put them together into a single set. So let's illustrate that on the picture. Suppose we have a certain universe, and suppose we have two sets in the universe, A and B, and these can be any two sets in the universe. Then the axiom of pairing says there is a set in the universe whose elements are exactly these two sets. So in other words, the collection of these two sets forms a set. And there is a specific notation for that set, um, which is as follows. So the set formed by the two sets is denoted like this. And the way we want to read this is the curly brackets here refer to the, in this case, the set notation. And basically between the curly brackets we are listing elements of the set, and the understanding is that there are no other elements apart from those that have been listed. So for example, by the axiom of equality of sets, um, something like this must be the same as something like that. And in the case when A is actually equal to B, um, something like this, which now, because A is equal to B, becomes this, is the set consisting of A as its only element, and therefore it can also be written like this. So that's what axiom of pairing says. Any two sets that we have in the universe, we must be able to pair them up into another set. And what is interesting about this is that because this applies to any two sets, now we can kind of repeat this procedure iteratively and get quite a lot of sets out of a very few starting sets. For example, if the axiom of empty set holds in a universe, then we know that there is empty set in the universe, right? Now we can apply axiom of pairing and pair empty set with itself. So this is this scenario here where A and B are equal to each other, and then we get a set that has one element, and that element is the empty set. Note that there is a difference between the empty set and a set having empty set as its element. The difference can be visualized by drawing where the empty set is represented um, as an object which expands into a collection having nothing in it, whereas a set having empty set as its element is a different drawing. It is this drawing where now that set, the empty set, has been included as the element of the new set. So this new set is definitely not empty, right? It has an element. Its element is this set, which is the empty set. So there's a big difference between empty set and the set having the empty set as its element. And once we build that, now we can proceed and build other sets out of this, right? We can now apply the same idea, take this as a single set, pair it with itself, and this way create another set. Now that one will have one element, which is the set having one element, which is the empty set. So in a drawing, it's attaching another circle here and designing a set as a result. And this process doesn't have to end. We can continue this forever. And this way, we are going to get infinitely many sets, in fact, right? So, and the number of this, I mean, at each space, we've got the set determined by the number of the curly brackets, right? So here we had no curly brackets. one curly bracket, two curly brackets. So this kind of tells us the depth of the picture, how long the picture is. And in this way, actually, we can in fact think of this as a way of encoding natural numbers in set theory. So if we have a universe of sets with the empty set and the axiom of pairing holding, then we could actually think of numbers in terms of these, where the empty set is declared to be, is defined to be the number 0, and that is defined to be the number 1, and this one is defined to be the number 2. So always the number will match the number of brackets in the notation for the set, number 3, and so on. So you can already see now here um, an application of the idea of a universe of sets, where we've created a universe where numbers can be defined. So numbers are no longer primitive objects. They are themselves defined in terms of sets. And another thing that's interesting about set theory is that in the beginning of this process, right, we had nothing, right? This yellow collection is nothing. There's nothing in it. But out of this nothing, we are building something, a set of nothing. And then, once we have something, we build another thing from it, a set containing that thing as its element. And you see, we eventually build quite lots of things. We build all of natural numbers and more than that. So, in a way, set theory allows you to create the whole world of mathematics out of basically nothing. And that is the nature of mathematics in terms that mathematics is kind of um, built out of nothing. Um, and that corresponds to the idea that mathematical objects are not like physical, real life objects. They are inherently abstract objects, and maybe all of this kind of tells us that after all, nothing is also something. So on that philosophical note, I'm going to complete this video here on the axiom of pairing.